So continuing on, let's take a look at now the cyanide ion, which is Cn with a negative charge. So once again, we don't really have a central atom, so we're just going to have carbon bonded to nitrogen. So let's count up our number of valence electrons. Carbon has 4, nitrogen has 5, but then notice this is an ion. This whole thing is a -1 charge. Negative charges mean that there are extra electrons, right? So -1 means that there is 1 extra electron in there. So we have 10 valence electrons total. So once we've got that, we move on to step 3, which is get them bonded using a single bond. That takes care of 2 electrons, which brings us down to 8. So now, doesn't matter if you start with carbon or nitrogen, let's just start placing those electrons to satisfy our octets. There's 2, 4, 6, and then 8. So I've used up all 8. I'm down to 0. I can't place any more electrons on here, but as you can clearly see, nitrogen is not satisfied, right? Nitrogen only has 4 electrons around it, which is 2 here and 2 here. It wants 8. So what we need to do is we need to start pulling electrons from carbon and putting them in the middle here. So if I take these 2 electrons, arbitrarily I took those 2. I could have taken any of the 2. But if I took those 2 and put them in the center, now nitrogen's a little closer to being satisfied, but it still isn't. It only has 6 electrons where it wants 8. So we would have to take another pair of electrons and stick them in the middle to form a triple bond, right? And so now we count, first of all, how many electrons do we have? 2, 4, 6, 8, 10, which is what we started with. And if we count up, are the octet rules satisfied? Carbon does feel like it has 2, 4, 6, 8, and so does nitrogen, 2, 4, 6, 8. Now it's kind of drawn a little bit, so this is just my OCD killing me. I'm going to redraw the electrons. You don't have to, but I'm going to redraw them like this, because in my brain that's just how I need to have it. But as long as you have the right number of dots, that's fine. One other thing that we have to do, whenever you are drawing a Lewis dot structure for an ion, remember that you have to put brackets around it, and then you need to put the charge on the outside. So in this case, -1. All right, let's take a look at this next one. Now this next one might be a little confusing for some students. They say we got hydrogen and carbon and oxygen, and they try to do maybe something like, oh, are we bonding things like this? No, that's not the way we think about it. There's a central atom in there, right? What's the central atom? Well, it's not hydrogen, you know that. It's either carbon or oxygen. Well, which one? Well, carbon is the least electronegative out of those. And if you remember, carbon is a common central atom. When you see carbon, it is the central atom. So that means the other elements, meaning that oxygen and the 2 hydrogens, are around it. Now, once again, reiterating, it doesn't matter where you put the oxygen and the hydrogen, so long as they're all going to connect to carbon. Okay, so let's go ahead and start counting up my number of valence electrons. Give ourselves some more space here. Let me erase everything. There we go. All right, so we have carbon has 4 valence electrons, oxygen has 6, hydrogen has 1, but there are 2 of them. So it looks like we have 12 valence electrons. Now let's get everything bonded using single bonds. So 2, 4, and 6. So we have 6 electrons left over. Well, the hydrogens are already satisfied, because remember, they can only hold 2. So with those 6 electrons, I'm going to start taking care of oxygen. 2, 4, 6. So we are out of electrons. So if I had any electrons left over, I would put them on the central atom carbon, but I don't. So at this point, I have to ask myself, are my octet rules satisfied for all my elements? Well, it is for the hydrogens, and it is for the oxygen, but it's not for the carbon. Carbon only has 6 valence electrons. We need 8. So I don't have any electrons left over, so the only way I can do this is by pulling it from another atom. Well, hydrogens don't have any lone pairs for me to pull from, so the only option is to pull a set of electrons, or in other words, a lone pair, and put them in the middle, making a double bond. Now, do I have the right number of electrons? Well, 2, 4, 6, 8, 10, and 12, which is what we started with. And all my octets are now satisfied. So I have drawn a successful Lewis dot structure. All right, keep moving on. We now get to OCN negative. OCN negative. As you can guess from the based on the previous example, carbon is in the center, and we have oxygen and nitrogen. So let's take a look at what we got here. Oxygen is 6 valence electrons, carbon is 4, nitrogen is 5, and then I'm throwing a 1 in there because it's a -1, so it has 1 extra electron. So total, we have 16 valence electrons. If I start with a single bond, that takes care of 4 electrons. We're now down to 12. So with those 12, let's take care of the oxygen. 2, 4, 6, 8, 10, and 12. So I used up all of my 12. I'm down to 0. So now my oxygen is happy, my nitrogen is happy, but my carbon is not. You see how my carbon is not happy? It only has 4 valence electrons, but I don't have any electrons left over. So, as you may have guessed it, the only option we have is we can do multiple bonds. Now I'm going to make some room for myself because you're going to see I'm going to need to do something here. So now at this point, this is something new. We know we're going to need a multiple bond, right? But we have options. We can pull from either the oxygen's lone pairs, or we can pull from the nitrogen's lone pairs, or we could pull from both. So let's take a look at this. Here's the first option. What if I pulled all of them from the oxygen? So if I pulled these 2 electrons and put them in the center, and then I pulled 2 more sets of electrons and put them in the center. Here's an example where we have a valid Lewis dot structure. Notice my oxygen has 8 valence electrons, my carbon has 8 valence electrons, and my nitrogen has 8 valence electrons. I also, if you count, have the 16 that I started with. 2, 4, 6, 8, 10, 12, 14, 16. So I have a valid Lewis dot structure, obviously once I put brackets. However, that was only one option. The other option was this. So right before I started making multiple bonds, I had this, right? I chose to pull all the electrons from oxygen. I could have done the same thing with nitrogen. I could have pulled these 2 electrons from nitrogen, put them in the center here, and I could have pulled another set of electrons from nitrogen and put them in the center. Essentially do the exact same thing, only do it on the nitrogen side. With brackets around it and the negative on the outside, I have a valid Lewis dot structure. All my octets are satisfied, and I have the correct number of electrons. Finally, there is actually a third option. So once again, this is what we had before we started doing any double bonds or triple bonds. Rather than taking all the electrons from the oxygen or all the electrons from the nitrogen, you could have split it. You could have said, okay, I'll take this lone pair, put them in the middle, but then also take a lone pair from nitrogen and put them in the middle. Now, I still have the same number of electrons, 16, and all my octets are satisfied. Every element has 8 valence electrons. So you can see there are actually 3 ways that I could have drawn this structure. When this happens, this is what's known as a resonance structure. So resonance structures occur when a molecule can be drawn in multiple ways. Now we're going to cover resonance structures a little bit more in detail in another video, but for right now, keep that in mind. When an atom or when a molecule can be drawn multiple ways, that's when you have a resonance structure. For this particular example, I would say that there are 3 resonance structures for this particular ion. All right, I want to give you a chance to try some on your own. So what I want you to do is I want you to pause the video and I want you to try to do carbon dioxide or CO2 on your own. Go ahead and hit play when you're ready to see the answer. All right, so go ahead and check your answers with what you got or what you see here on the screen. Probably most of you, if not all of you, did this first one right here, because if you're anything like me, you like to see that, it's symmetrical, right? You have the two double bonds. But technically speaking, you also could have drawn it this way, or with the triple bond this way. So if you take a look at these three, you'll notice that all three of these are valid Lewis dot structures because, number one, they all have the same number of valence electrons, which is 16. And number two, all of the octets for every single element are satisfied. It does have the 8 valence electrons that it needs. So there are technically 3 resonance structures for this particular molecule. Now, like I said, the most common one is probably the one that you saw first, but there are 3 resonance structures, and that's important to know. You notice that when we have resonance structures, you draw this double-headed arrow in between every single drawing. The brackets are not needed because this is not an ion. Now, for the next one, I'm going to quickly show you. I want you to draw CS2. Okay, CS2. Now notice CO2 and CS2 look a lot alike. They both have carbon, and they both have 2 of the second element. Do you notice, look at your periodic table. Do you notice how oxygen and sulfur are in the same group? Because they're in the same group, they are going to bond in the same way, and that's because they both have 6 valence electrons. So if I asked you to draw the compound CS2, we could actually do that very simply by simply replacing every oxygen with sulfur. I don't even have to think about it. I already know what it's going to look like. And that's a valuable tool. You can use that to help you solve a lot of these Lewis dot structures. Let me give you another example. We're not going to work it all the way out, but what if I gave you the compound PCl3 and I wanted you to quickly draw that Lewis dot structure? Well, notice how PCl3 looks a lot like NF3, right? And you notice phosphorus and nitrogen are in the same group, and chlorine and fluorine are in the same group, and you have 3 of each. So because of those similarities, PCl3 is going to bond exactly like NF3. So we could easily just replace nitrogen with phosphorus and fluorine with chlorine, and you would have the correct Lewis dot structure. All right, we're going to go ahead and do these last 3 in the next video.